In the last lecture, we talked about uncertainty in the prediction of future climate. Okay? And that uncertainty has various components. One is scenario uncertainty. We don't know how carbon dioxide is going to increase in the future because nations have not yet made commitments to cut down their carbon dioxide emissions. So, we have to predict how nations will behave. So, there is scenario uncertainty. Even if the scenario was certain, we saw that models are not perfect. Models have certain weaknesses. So, when you project the future temperature or future rainfall, there will be an error bar. There will be some uncertainty about our estimate of future temperature or rainfall. And then if the model resolution is not very high, we will take the model output and downscale it. That downscale can be done statistically or through a model. That will introduce some more uncertainty. Okay? Then finally, you will take the model output, let us say rainfall, and try to predict floods in a given area. So, for that you have to use another model which takes rainfall as the input and its output is, let us say, the level of the river in a certain place, okay, flood. That model also has some uncertainty. So, there is a cascade of uncertainty. We have to know that clearly before we tell anyone that this is the model output. We have to make it clear what are the various sources of uncertainty and what is the error bar within which we can predict these quantities. Now, one example of this is shown here from the work of Hawkins and Sutton, published 15 years ago, in which they are looking at as a model integrated over the next, let us say, 90 years from present condition, what are the fraction of the total variance due to. Okay? Initially, when you look at the model output for the next 10-20 years, how well you assimilated the initial data is relevant. Okay? Every model, when it starts, you have to assimilate whatever data available at that time, and if you do it properly, it is okay. Otherwise, there is some uncertainty in the initial condition, which will be there for quite some time, maybe 20-30 years. Okay? Then of course, the model itself has certain problems. So, the model uncertainty also will be quite large in the first 20 years, but as the time goes along, the major uncertainty is the scenario, what emissions of carbon dioxide will take place over the next 90 years. Okay? So, you can see that if you want to know what will be the temperature of the globe 70-80 years from today, then the major source of uncertainty is not the initial condition, it is not the model. Model contributes around 20%. The major uncertainty is emissions. That is why it is wrong for people to say the models are not accurate, we can't trust the future. The future depends on us, depends on how much CO2 is being emitted globally. That controls the path we are going to take. Of course, there is some uncertainty due to models not being perfect, but that is only 20%. 80% is due to the scenario. So, this must be kept in mind whenever we discuss policies, when we discuss with people, because very often people say we cannot trust models because they are not accurate. That is partly true, but if you look into the long term future, then our problem is not the model or the initial condition, but the emission scenario. That is how nations control the amount of CO2 that they release. So, the point made by Hawkins in this paper is because of initial condition uncertainty and nonlinearity, there is certain number of uncertainty which is irreducible. Okay? So, prediction of the future is not perfect, that everybody understands. So, the point is very important. If you want to know what is going to happen in the next 20 years, then climate change signal due to the increase in carbon dioxide rarely emerges from the noise of natural variability in the climate. Okay? So, this is very important because we find lot of non-government organizations, NGOs, put out various reports in which they claim to predict the temperature or rainfall in a certain district in the next 20 years. That is not possible because there is a lot of variability in climate due to natural decadal variability, and the impact of increasing CO2 does not emerge outside this variability. Okay? So, we can be confident about the impact of CO2 only if you look far into the future, okay? Not in the next 10-20 years. This is what makes this problem very difficult, because if you tell a policy maker that I cannot tell you how carbon dioxide will influence rainfall temperature over the next 20 years, most of them will not be interested in this issue, because they are not concerned what happens 100 years from now. But those of us who are serious about climate change have to be concerned about what kind of climate will be there on earth for our children and grandchildren. Okay? And so that can be predicted with some assurance, but not what will happen in the next 20 years. Now, this problem is more clearly stated here. This is a projected global mean temperature, and what is showing in orange is the variability due to natural variation, so called internal variability, and around that you have blue, which is the model uncertainty. Okay? And then comes scenario. Okay? Now, in this case he is showing a fairly large model uncertainty even at 2090 compared to scenario uncertainty. Okay? So, this depends upon the model concern. Okay? This is also in a Hawkins and Sutton paper published a little earlier. Okay? Now, if you this is the percentage change in the top figure is for rainfall. So, rainfall is very highly uncertain. The bottom figure is for temperature. There we see that the major uncertainty is this scenario green, and some uncertainty due to model in blue, and internal variability is very small. But if you go to rainfall, then the problem becomes very different. The major uncertainty is due to the model. Okay? So, I want you to remember the important difference between rainfall and temperature. Temperature predictions are much more accurate at the global mean level, but not rainfall. Now, this is a big challenge, because we ask anybody in India, the major concern is about rainfall, not temperature. Okay? Because the Indian society is very concerned about rainfall, because rainfall controls our agriculture. So, they would like to know how rainfall will change in the next 30, 40, 50 years. So, but unfortunately our ability to predict rainfall is not as good as that of temperature. So, I want you to keep this issue in mind, and so the same figure shown here is shown in another way here, showing the model, scenario and internal variability as 3 different lines, and the sum of these is the total. And again you see that model uncertainty is large in the case of rainfall, model uncertainty is smaller, and scenario uncertainty is larger. Okay? So, as far as global mean temperature is concerned, what temperature we will have in 2080 depends on how we control our CO2 emission. Okay? But when it comes to rainfall, we are not very confident. In rainfall, scenario plays a smaller role than the model. So remember that rainfall is going to be the biggest uncertainty in our ability to predict the future, and that is of course not very good, because in a country like India and many Asian countries, rainfall is considered a more important parameter than temperature, because in an agricultural society, rainfall controls the life. Now here, from the same paper by Hawkins and Sutton, we are looking at decadal mean precipitation. On the left is global, on the right is regional. This is Sahel, that is North Africa. Okay. This graph is shown to tell you the difference between global and regional. You can see it in the case of global rainfall, the major uncertainty is of course model, and scenario has some role. But you come to Sahel, North Africa, the June, July, August decadal mean rainfall model is still the major uncertainty, but the initial condition also plays a role. Okay? Internal variability, that is the model's decadal and other variability. So the difference between global and regional is that in global, scenario has some role. In regional, the role of scenario is very, very limited. So when you talk about India or Africa nations, then we shouldn't worry so much about scenario. We should worry about how good the model is in predicting rainfall. But when you compare, instead of Sahel, you compare Europe. You can see Europe is somewhat different from Sahel. In Europe, the major uncertainty is the natural variability, internal variability, and of course model uncertainty. And you come to Southeast Asia, which is similar to India, you can see that even scenario plays some role, but the major role is model. So what I want you to understand is, as you come to the regional scale, our problem is that in predicting rainfall, the major problem is the model's accuracy. Models are not accurate in predicting rainfall on a regional scale, although they are quite good at the global scale. So this issue must be remembered, that the major uncertainty about the future rainfall comes from the model, because model have not yet become accurate enough to predict with great confidence how will rainfall evolve 30, 40, 50 years from now on account of the increase in carbon dioxide. Now here is a comparison between two different scenarios. In the IPCC scenario, one in which there is high emission and when there is low emission. Okay? If you go on the high emission scenario, we go on releasing more CO2 from about 40 gigatons now, 40 billion tons, to around 80 billion tons by the end of the century. But if you are more careful, you can reduce the CO2 emissions to around 0 or even negative. Okay? So when that happens, look at the CO2 concentration. If you go on what is called business as usual, don't worry about climate change, then your CO2 concentration will go from around 400 parts per million today to around 800 parts per million. While if you curb our emissions, you can maintain it to almost around 400 by 2100. Now what is the consequence on temperature? The temperatures today is around 14.5 or 15 degrees centigrade global mean, and you can see that if we are able to curb our CO2 emission, we will be able to maintain temperature within about a degree. Okay? But if we don't do that, we can go up to 2 to 2.5 degree warmer. So, this shows clearly that the kind of future global mean temperature we will have at the end of century depends totally on what we do today. And this is what the IPCC is trying to convince all the political leaders around the world in Paris, that it is in our hands to determine what will happen in the future global mean temperature. We can do it provided we reduce the CO2 emission from around 40 to 50 gigatons to either zero or negative emissions. Okay? Now, if you look at the global mean temperature and especially rainfall in the future, let's look at June, July, August, which is relevant to India and many Asian countries. You can see in this graph they are showing June, July rainfall change in percentage in the last 20 years of the present century. And in this graph there are these hatched lines. The hatched line says that we are not so sure about the change, okay, because models do not agree. Okay. There are about 35 models which predict the future and they do not agree on the amount of change. So, you can see that over some ocean regions like Equatorial Pacific and parts of Arabian Sea, Antarctica, we are confident what will happen. Okay. In Antarctica, of course, as the temperature goes up, rainfall will increase. But over most other parts of the world like South Africa, Australia, Europe, we are not so sure because models do not agree on the amount of change in rainfall. So, again I want you to remember this important point, that although we are confident about temperature prediction about the future, both regional and global, we are not so confident about rainfall. Okay. So, let us summarize this. Climate models are reliable for the prediction of temperature, but not rainfall. Okay. So, this must be remembered when you make any decision with regard to policy. Climate models are able to capture decadal variability, but not variation from year to year. For example, even today our models cannot predict what will be the monsoon rainfall next year, which is very tough. Okay. But we can make some prediction about what will be the mean rainfall average over 10 years in the future. Okay. And we saw that climate models become more realistic when model resolution goes below 20 kilometers. Right now most models have grid sizes of order of 50 by 50 kilometers. That is not sufficient to predict rainfall on a regional scale. And models are not good at predicting local impact of climate change compared to global, because when you come to local impact, you not only have to worry about the carbon dioxide increase, you have to also worry about changes in land use, changes in air pollution, okay, which is very local. Air pollution is a local phenomena, carbon dioxide increase is a global phenomena, okay, because carbon dioxide released any one place in the world goes everywhere and mixes almost uniformly. So, local impact can be done accurately provided the models have resolution below 20 kilometers and we are able to specify how air pollution control will happen in the next 10-20 years. We can't predict that, you can't predict the future. Okay? So, people demand local impact because that is what affects our life, but local impact is much more difficult because models have to be at a high resolution. You need to provide information about how local land use change and local aerosol emission will change. For example, take Bangalore as a city, it will be difficult to predict what will be the temperature and rainfall in Bangalore by 2035 unless I know how Bangalore will expand and which part will become concrete and which part remain green. Unless we know that, you cannot predict the future rainfall in Bangalore. Okay? And temperature also is tough because when you put more concrete, the temperature rise will be higher. Now, you must also remember that predicting the temperature of Bangalore in the next 20 years is influenced by natural variation, okay, which occurs because heat is exchanged between ocean and atmosphere continuously. So, year-to-year changes in temperature occur. There are natural variation like El Nino in the Pacific. There is a Pacific decadal oscillation. There is atmospheric, there is Atlantic decadal variation. All these things are not predictable easily on a year-to-year change. Okay? And smaller spatial scales and smaller time scales expect more natural variation. Okay? And signal to noise ratio, which is very important for our confidence, is much lower for smaller scales and larger scale. If you take global mean, you can predict very accurately about the future role of carbon dioxide or sulfate or even solar radiation, but not on a regional scale. And temperature has a better signal to noise ratio when compared to rainfall. Rainfall is always more difficult because it varies a lot on the smaller spatial scale. Now, this is shown in this figure from IPCC, which has what is called frequently asked questions. So, I strongly urge you to look it up. They are very nice graphics that they give so that most people can understand the impact of climate change. Here they are showing that the correlation between the air temperature, global mean, and different models, older ones and newer ones, the correlation is very close to 1. Okay? So, temperature, global mean, we are very confident. But you come to rainfall, you see already there is a large reduction in the correlation from 1 to around 0.8. And you come to sea level pressure, there is even larger variation, because sea level pressure depends on how temperature in the ocean varies and depends on how much heat is absorbed in the ocean and how deep it goes. Okay? So, you can clearly see that between the global mean temperature, rainfall and sea level pressure, there is a big difference in our skill. Skill is very good only in the case of global mean temperature. You go to rainfall and you go to sea level pressure, our confidence goes down. Okay? So, let me conclude today by saying society's perception of climate variability and climate change is largely formed by frequency of extreme events. Since extreme events have a large negative impact, but our ability to predict extreme events is not good. As the climate model resolution and treatment of process improve, the simulation will improve, but will still be limited. Okay? Thank you.